Всем доброе утро еще раз. Меня зовут Дима, я работаю в Фейсбуке. Сегодня я хотел бы рассказать про систему для хранения и обработки логов. Доклад я делаю на английском, много терминологии. Поехали. Hi everyone. Today I want to discuss a LogDevice, a distributed data store designed for logs. First of all, why do we need specific data storage for this type of data model? And it comes from a fact that actually logs are pretty simple and they're quite different from regular files. And I will explain how are we using this and how are we trying to achieve better efficiency and better durability of a system using these facts. Okay, first of all, what is a log? A definition. This is basically a systematic recording of events, observation, or measurements. And it actually have a broader application than what we used to work with the logs every day. So let's look at what type of logs can we have. It can be replication logs. This is a really common case of how we try to replicate data across different data storages. Write-ahead logs, of course, transaction logs, and even the message queues can be represented as a logs. Let's take a look on a basics workload with the logs. So first of all, it's sequential. It have records appended to it. Record can be different size. It is append only. We only append new records at the end of a log. And it's append only operation. Second, when we read, we usually specify a first point from where we're going to read, and then we sequentially reading data from this point. And of course, there is a trimming operation, and that's how we delete logs. And we only can delete logs from oldest, from the beginning of the log, and we just trim them one by one or in groups from the beginning of the log. Let's take a look at the target use cases that we use at Facebook for this system. So it can be a reliable communication between services. If we have several services which trying to exchange data, it have to be durable, right available, and fast. The system can be used. Write-ahead logging is also can be a use case. State replication, as we mentioned before, and journaling any actions for later execution. Let's take a look at one case a little bit more deeper. So let's say we have a database, just a normal database, and we receive any type of update. It can be any user action or other type of update. It goes to index update service. So yeah, overall this example is how we try to sustain a state for graph index. And yes, first step, it's update is getting into the database. Second step, it's going to index update service, where it's transformed, resharded, and getting prepared, and then it's just sent to LogDevice, our system, which is later propagated to index to be updated, secondary index. The main use case here is that we want all of this to be really fast. It had to be in order of 10 milliseconds. The reason is that we want to have all these updates being available for user as soon as possible. So if I take an action on a Facebook site, I want to be able to search for it, or I want to be able to have this change being available for me in a matter of milliseconds. Let's take a look at different examples. It's a system Scribex used at Facebook. It has a little bit different use case. So this is an example of a fire and forget system where we want to send some data, we want to record some, we want to save some changes, save some log in a system, and we just continue execution without waiting for message that this change is being saved. For example, on PHP code, you just save some data, log some data, and you just continue execution, and you hope that this data is going to be saved. You don't wait for it, and you don't wait for delivery for message that tells you that data is stored. So how this works? So first of all, we have a Scribex process. This is a local process running on a machine, which is actually sending this update. This process buffer this data, batch, and then send it to loaded to Scribex routers. The reason why we have this local server is local process is because if we lose like network, if we cannot connect to Scribex routers, we can still batch, we can still have it locally, and once we are ready to send, we can actually send it and propagate it further. And then after Scribex, it gets sent to LogDevice, and from LogDevice, it can be read by Ztails special processes, and later being available for consumers, or just saved in data warehouse for later processing. Sorry. So in this use case, the biggest challenge is throughput. It can be terabytes per second. This is a huge system widely used across Facebook, and it has a huge throughput. And moreover, we're actually not really interested how fast it's going to be propagated. We want to send this log from some endpoint, and we hope that it's going to be delivered to data warehouse or consumer at some point for later processing. It can be any type of logs, any type of analysis we want to take action on later. So as we can see, there is actually quite controversial goals we're trying to achieve with this system. For example, we want to have a high throughput. At the same time, we want to have a really good end-to-end latency. And we cannot achieve both. We have to be able to choose our best configuration. Or it can be how fast we can append, and how durable is our records. And it also has to be configurable. So LogDevice have a lot of configuration which helps you to achieve the goals you're trying to, the goals you have. But actually there are some things which is common for all the use cases. First of all, high write availability. We want to accept data, and we want to be able to accept it no matter what. Durability, of course, that we don't want to lose data. This is a pretty big challenge and pretty big rule we try to follow. Also, we've seen that many clients want to replay and read huge amount of data, old data. So I'll talk about this later and how we dealing with this. So there is also consistency requirements. For example, we deliver records in the order of the sequence numbers. So if I send the record 1, 2, 3, I want to be able to read in the same sequence number. I want to read 1, 2, 3 sequential. I also want to be able to repeat my reads, read the same data again, over and over again, and maybe using multiple readers. So what are our workload expectations? First of all, it can be really spiky. Some particular logs can have a huge spike, 10x or 100x of like for some particular logs, and we have to be able to still maintain a system and store this data. Of course, we have to support multiple writers per log. And we should be able to handle massive occasional backlog reading. When client says, I want to read data from one day, like 1 day old data, all of it now with multiple readers. And we have to be able to support this. And of course, there is millions of logs. So in practice, we have thousands or hundreds of thousands of logs, but we can support up to 1 million of logs. I want to mention then that supporting 1 billion logs, it's a different problem, and we're not trying to achieve it here. So now, interesting question: how are we going to do all of this? So I just highlighted what are our goals and what we're trying to achieve, and now let's actually take a look at how we're going to do this. First of all, that we're going to use the fact that logs are much simpler than files. Let's compare just a POSIX file and a log. First of all, for file we can write anywhere. For logs, it is just append only. But of course, there is many file systems which can support append only operations, but there's more requirements on logs. So second is it's a sequential byte numbering. So it means that if I write 10 bytes and then I write next 10 bytes, I expect it to be sequential data in a file. In a log, actually, it can actually be, each record can be actually, can have some gaps between, and this helps us to achieve a better write availability. I will talk about it later. Space reclaim, like the way we delete is also different for files and the log. For log, we can just trim old records. For file, it's deleting files. It's pretty different. And for POSIX file, we should support random access. For log, it's usually sequential reading and the writing. So let's look at its API, which LogDevice provides. Append is, for append, you just specify a log ID and the payload, and you receive a log sequence number, which is a number which is assigned to this log. If this, for this record, which is sent only when record is stored. start reading, you specify a log ID and log sequence number. And you also specify a last sequence number where you want to stop reading. If you specify just max, it means that you want to tail. You will read and you will stall maybe at some point, but once writer add more records, you start getting more records. So this is just a way to tail this log. And of course there's a read, which you specify how much you want to read, and you receive records, or you receive a gap indicating a data loss, or that you might trying to read from data which is already trimmed. I will talk about gap later. So which principles we are trying to, which principles we have for our system? First of all, it's separate sequencing and storage. I will show how sequencer, which is a process of getting data, getting appends, is independent from storing. We try to separate these two processes. Second is try to maximize placement options. So when we receive a record and we have a cluster of machines, we are actually trying to store this record. We want to be able to store it to multiple machines, and I will show how this helps later for write and read path. And of course, we have a fully distributed metadata. We use Zookeeper for this. Okay, let's take a look at example of writing and reading in LogDevice. This is going to be interesting. First of all, this is actually how a server, how individual racks look like with the servers in it. It can be like racks like this can serve a LogDevice cluster. So we have a server, we have a rack containing these servers. Let's see how, if I'm a writer, how will I append the record? First of all, I have to pick a machine in a cluster, in LogDevice cluster, where I will save this append. And this machine is not specific for a log. It can be changed, but we know where it is. So we found some machine and we send some message to it and to some log with message foo, let's say. Let's look inside. When we're trying to append this message, we're trying to assign a sequence number for it. And this is interesting that we divide it by two. First number is epoch number, and second number is a record number, sequence number inside of the epoch. Why this is important? Because if we lose the sequencer object, a new sequencer will pop up on a different host, and we will just bump epoch number, and then we can continue writing. We don't have to wait, and we don't have to try to achieve, try to find out what is the next sequence number. We don't guarantee that it's going to be that it's going to be like +1 all the time. It can be just next epoch. For example, this is records we stored. It have epoch number 3, saved record 5, 6, 7, and then our sequencer died, or some failure happened, and we have a new sequencer running on different machine. Before we have to finish a recovery process and all of this for previous epoch, but we don't want to wait because our clients want to send data now, and it expect to be saved and to be appended. So we just bump epoch and continue saving data, appending it. This is actually a big design decision which will play a big role in different aspects I will show. So let's look at the writer. When a writer sends an append message, there is an appender object, which is appender object is trying to just save this record to multiple machines, and we want to save it for multiple machines because we don't want to have a single failure. We want to make sure that this record is saved on multiple machines, and we want to be able to find it even if something failed. Let's say we have a appender object with the epoch 3 sequence number 5 start appending. At the same time, if a new writer sends us a new message, we have a next appender object working on saving this. And they can work at the same time. They can work in parallel. We don't wait. We have a window of appenders which can be working at the same time. We start with always available to get new and new appends. So now this is an interesting concept about non-deterministic copy placement. As I said, let's say we have a appender in some machine, and we're trying to actually save a record, save a message we're trying to store. We select some like 3 or number of replicas machine, random machine in a cluster. And once we select it, we just send the store messages to them. I want to point out that it's random, it's not pre-selected. This is a big difference with the other systems. This helps us to actually have a really good write availability. We can store them by sending the record directly, or we can use this daisy chain algorithm to actually send it in a chain fashion, so that machine which have a sequencer on it is not overloaded with network. Let's look at the record format. First of all, logid, then of course LSN. Then we also store a copy set, which is telling us which machines have this record. For later, it will help us to find this record. We also have a timestamp, and of course, payload. So let's look at the concept of node set. As I said, we can store our record into 3 random machines, but actually there are some constraints. We don't want to be able to store it to any of 3 machines. We're trying to select a node set. So for each log, we say only these machines are going to be available to select a copy set in it. And we can see that one log have this one node set, second log have different node set. They can intersect. We can also see that there's we try to have different machines, different racks. So this is 3 racks, and we're trying to have machines available on different racks. So if there's a failure in one rack, we can still have like some options where we're going to select our copy set from. What is good that we actually can always add more machines to copy set. For example, one log is having a huge load, spikes of load that have too much data being appended. We can dynamically grow our node set. So this is the machines which are going to be available to write our records to for one specific log. So once we select three random machines for one log. Yes. So sorry. So within this node set, machines can be selected randomly. Also, we can actually define some rules. For example, I want my data to be stored I want my data to be replicated across different data centers. For example, there is a Prineville or Altoona and the Fort North data center, Facebook data centers, and I select my node set so that I have machines available in all of them. Moreover, I can say that I want my copy set to be at least in 2 data centers, so that if there is a huge outage and we lose a whole data center, we can still read and write our logs because copies are stored across data centers. So let's take a look at how are we dealing with failures. Let's say we're trying to save one particular record, epoch 3, sequence number 5, and one machine failed to store it. We can always select a different machine and repeat our operation, and our appender is going to try to store it until it's succeeded. Once it's stored everything, we can send a message saying our client, okay, we saved it. Here's your sequence number, and the data is stored. Now, interesting question is, how are we going to read this data? So the big interesting point here is that reader is actually going to connect to all machines in node set. But as I said, node set can dynamically change, and it can be new machines added, or we can increase it, or we can just change it, reshuffle. In this case, reader will take a look at the metadata and decide and understand which all historical node set it need to access to read data from A to B. And then it will just have a union of this node set and connect to all of them and start reading records. What's interesting is that records start arriving from these boxes, and they may not be sequential. Each box will try to deliver whatever it has. And later on a client side, so on a reader side, we actually can take a look which data we received, and we can remove duplication, rearrange it, sort it, and have it ready for a client in sequential matter. So if there is a data loss, if there is a data loss happened in a records, we can actually have a gap, and the reader on the read side, it will detect that there is missing record and have a gap placed. And this gap is going to be available at this record during read API call. So what efficiency features we have? First of all, client and server side batching. We have a batching, and we have a ZSTD compression. This ZSTD is the latest Facebook compression algorithm. Also, there is a server-side copy-set filtering for single copy delivery. This is interesting. When we connect to all node set and we say that we want to receive record number 35, then we actually don't have to get it from all 3 of the machines have it. There is optimization where one of the machine understands that this machine responsibility is offended. So we will actually have only 1 copy, and this will reduce our network overhead. Also, there is one more optimization of copy set stickiness, and And it means that when we have a copy set, when we select three random nodes, actually we will try to stick to these 3 machines, because it means that data is going to be stored on these 3 machines sequentially, and it's going to be actually really effective on a disk on a disk overhead. Let's take a look at the LogDB. Actually, this is a data storage we're using locally to actually store the data. This is optimized version of RocksDB. RocksDB is open source data storage, local data storage, also made by Facebook. So which features we want to have from local log store? Of course, high I/O. Everyone wants this. Mostly sequential I/O patterns on a disk, because our records are sequential data. We want during reads and writes, we want these operations to be sequential as well on hard drive. Low write and read amplification, which means that we try to read and write as little as possible. Again, because we work with HDD mostly. In LogDB, we store our data in a following format. We have a key, which is log ID and LSN. We have a copy set, timestamp, and payload. So let's take a look at how LogDB insert new records. So LogDB first storing them in a RAM to make it efficient, and it's stored as a mem table. Basically, it looks like a list, and once we start getting new records, they actually sorted already in RAM. And let's look how we store records for A1 and B and for A and B logs. And once it gets big enough, we actually flush it. We flush all this. We flush all this memory in a RAM to disk, and we store it in a SSD file. And then we start getting more and more SSD files because we flush our RAM. I want to point out that to make sure that we don't lose data when, for example, power goes off and our RAM is clear, we have a write-ahead log. So let's say we have several SSD files. Now we have, for example, 4 files. And if our clients say, "Hey, I want to read a record. I want to read all records for log B," then at this point we have to actually tail all 4 of these files on a disk, and it means that we have 4 iterators on our disk reading sequential data, which is not efficient. And that's why RocksDB have compaction. We actually merge them in background. Sometimes we say, okay, we have too much of these small files. We don't want to keep these iterators. Let's actually merge them to one big file. In LogDB, we solve it differently because compaction is actually really heavy operation. If you try to compact thousands of files in one huge file, it can be pretty heavy on a disk. So because of our structure, which is logs, we are going to have partitions, and we store data in partition. And when we have a reader, we only read for one partition. And then once we finish reading from one partition, we move to another partition, and another. So we don't have to maintain iterator for all of these SSD files. And one of the biggest advantage is that when we drop our records, we don't have to go and remove each single of these small records in each SSD file in each partition. We just drop entire partition. Once all the records we have on a disk is not like the retention is gone, we actually drop this whole partition. So if clients say, hey, I'll send you this data, but keep it for 1 day. Once 1 day is over for these records in partition 1, which it can be, partition 1 can be like 15 minutes, we just drop entire partition when each record there is expired. And this is much more efficient. Yeah, or sometimes we can actually compact all this partition. So there's a lot of failure handling, and I don't want to go too deep in it, but first of all, there's a gossip protocol. Machines gossip with each other to detect any problem with the machine, any failures. And we have a write availability restored within a seconds after failure detected. And we have a process called log recovery. And once one sequencer dies and new one pop up, we actually try to recover what have left in this previous sequencer. And of course, there is rebuilding. Interesting process of rebuilding. If a disk or like a node goes down completely, we can't recover data, we have to rebuild it. So we have to restore the replication factor of records after a node or drive failure. And this is interesting that once node failed, we lost this A and B and C. These records, A, B, and C, they have now replication factor 2 instead of 3. So we have to restore it. And the way we do it is we communicate with each other. Clusters are communicating and doing many-to-many rebuilding to restore this and send these records, missing records, to have restored replication factor. I want to point out how efficient it is compared to just bring a new machine and start writing everything to one machine. Because if we just place a new machine and said, hey, everyone send missing data to this machine, it will be overloaded because it's going to be terabytes of data written to one single machine. And the single machine have to perform all this network and disk operation. That's why many-to-many rebuilding is so much more efficient. Yes, so that's what I was talking about. Not limited by capacity of a single node. Rebuilds 5 or 10 gigabytes per second. It's fully distributed, coordinated by RSM running on a special internal log, event log. This is interesting that we have our internal logs, which looks like normal logs, but actually it's internal logs for internal communication. So what's next for LogDevice? What new projects or what we're trying to achieve next is, first of all, disaggregated clusters. Interesting that appenders and storage nodes in our design, they're not bonded to each other. And we can use it as to actually have a different hardware type. For sequencer, we can pick boxes which has really good CPU and no storage. And for storage, we can have a really good flash drives with not so strong CPU and achieve better efficiency. So also, as I said, right now, appenders who are trying to append records and sequencer live in the same machine, but actually there is no limitation to separate them. And this way, CPU on this sequencer box is going to be much less overloaded. And also there is a project which is, with this project, previous one, this means that we can store much more data for single log. Our one single log can have a much higher throughput because it's not bounded by CPU. Sequencer is pretty light process. And once we have this, we can actually apply a filtering on records. It can be one log, but we can say, hey, there are some filters I want to apply. I want to filter out some data, and I have a marker saying in the key, as a key to say, to separate and somehow separate this one log. that's it for me. Thank you very much. Any questions? I don't think we have too much time, but maybe a couple of them.
Раз.
Hello, I have a question. What is the most often reason for machine to fail? So you say a lot of machines can fail for different reasons, but in real life, why machines are failing in clusters?
Thank you. Okay, good question. I think the important key here is that it depends on a scale. If there's thousands of servers, there can be just hardware failure, and we want to still survive it. This is first type. Second type is a power outage, or it can be actually kernel bug. I've seen a lot of different types of errors happening on a huge scale. If you think about like hundreds of yeah. If you have thousands of servers, a lot of bad stuff can happen. Yeah. Yes. I think microphone. Hello. Oh yeah. Okay. Works.
Раз.
A few questions. Like the LogsDB, it's a database that works on the server inside the rack, right?
So RocksDB, yes, it's a LogsDB based on RocksDB. It works on on each machine, on each storage node. It's a local database.
Got it. And the next question is where are you storing the metadata for all this sequencer stuff? Like
Zookeeper. You mean epoch? Epoch number and all of this, it's stored in Zookeeper, and we use a usually high replication number, so that we minimize our chance to lose metadata.
Okay, Dmytro, you said that you write to a random set of nodes. Hello? Oh.
Hey.
You told us that you write to a random set of nodes, and upon failure, how do you know what entries, what values should you redistribute?
Okay, so as I said, each record, when I send this particular record to 3 nodes, I have a copy set saved. So I send it to node ABC, and I will store I will save this ABC, and I will save it to A, to B, and C. So each of the machine A knows that, okay, I have this log, I have this record, machine B have this record, and machine C have this record. So later, if C fails, A can take a look, oh, I know that C failed.
Okay, got it, thank you.
Hello, thank you for your speech. How do you actually update copy set part of the record when you fail chain write or something like that?
Yes. So if I fail to store record to one of the machine in copy set, I actually send a completely new store message to new. It can be three new machines. It can be 2 same machines. If this is a 2 same machines and 1 new, then I will ask them to update information about copy set. So if A and B, if I try to save to A, B, and C, but C fails, I will do. also remember if one machine in we will not try to save it. We will not try to store new messages there for some time.
Давайте поблагодарим Дмитрия за его прекрасную доповедь. Сейчас у нас перерыв в 11:50. Жду вас здесь.